Okay, let's first briefly review what we have covered in our last week's lectures. Basically, we define the linear regression problem using the housing price prediction as an example. And when we introduce more features, more than one features, it is more convenient if we can represent the data, the features, and the parameters using matrix and the vector notations. Okay, so there's a concept which is important here, which is the dot product between matrix and vectors, or between two matrices. Okay, so it's basically the summation of the products between each item of the two matrices or two vectors being multiplied. And this will be the key operation that you need to use, need to call in the NumPy environments, so you can finish the first task of the linear regression programming homework. Okay, so as you can already find in that Jupyter notebook is that we actually have the second part of the task, which asks you to implement the gradient descent method. And for that method, we haven't covered it yet, so we're gonna go through the gradient descent parts in today's lecture. Okay, and then we are pretty much finished with the linear regression parts. Okay, yeah, let's look at the normal equation solution again. So the form of the normal equation looks like this, okay, which is actually quite easy to implement if you already know how to call the numpy.dots functions in Python, right? All you need to do is to pay attention to the dimensions of your inputs matrices, as long as you make sure that they are in the correct dimensions, and also don't switch the order of the matrix multiplication, right? Because that will directly affect the dimensions, that will directly change dimensions of your outputs. Okay, so whenever you have confused with which way you want to order the inputs arguments of an equation, then it'll be quite convenient if you can just check the dimensions of each component of your inputs. And in this example, we have 1, 2, 3, and 4 matrices or vectors in your inputs, right? So you just need to check the dimensions for each one and to see if the outcome of a product, if the dimension of that outcome actually matches with the next component in the equation. If it doesn't match, then probably there's a mistake in your implementation, or there's a mistake in the equation. Okay, that's a common, pretty common technique in either the mathematics or the implementations of the so-called deep learning area. Yeah, because at the end of the day, it's all about linear algebras and calculus. And for linear algebras to conduct correctly, dimensions is a very critical factor. All right, so we actually already get started in our last lecture by looking at the limits of the normal equation method, right? So it looks simple, but the underlying computation is actually a lot, especially when you have very large matrix. When your X transpose, say when your X have 100 columns, right? And the results of X transpose times X would also be a 100 by 100 matrix. And that is okay, right? The modern computers can handle it properly. What if we have higher dimensions? And that is pretty common in scenarios when we have massive amount of data, massive amount of raw data and heterogeneous data. Okay, so the computation of the inverse of a really large matrix, imagine there could be 10,000 by 10,000, right? Then that is really a slow process, okay? And most of the laptop computers cannot handle such computation easily. Okay, so that's why we introduce a second method for in this scenario for the linear regression problem. It's called gradient descent, and we already introduced the concept of gradients, which is basically equivalent to partial derivatives. Okay, and the partial derivative is something that you can compute in a similar way as a single derivative, but because it's a derivative with respect to a vector or multiple variables, okay, then you need to basically compute a derivative of the target function with respect to each component in your vector. Okay, when your input is a two-dimensional vector, then your derivative is also two-dimensional. Okay, so that's one thing we should always keep in mind. Whenever we talk about the derivatives of something, then it must be in the same shape of the original vector. The derivative with respect to that vector x is the same shape or same size or same dimension as that variable. That is really useful when we try to implement gradient descent in our next step. Okay, so now I need to quit sharing quickly and enter the player mode. Okay. All right. So we have gone through this page already. Yeah, so in two-dimensional space, or actually when you can only consider the derivative with against the one variable, and it's actually pretty easily defined, right? But the same when we extend the concept to higher dimensions, it's still easy in the when your inputs input is two-dimensional, as demonstrated here, right? You can imagine that your inputs to the function x and y is a two-dimensional vector. Okay, so for any kind of vectors, you can always visualize it if it's two-dimensional, just using an arrow, right, pointing towards the direction of that vector. Okay, so but it's a function that takes two inputs, two-dimensional vector as the inputs, and the surface of the function, of course, vary depends on the nature of the function. But for basically any type of functions that is differentiable, you can compute the partial derivatives of that function with respect to the two-dimensional vector, with respect to each component of the vector, right? So, which is different. The third demonstration here shows a difference from how we should visualize the derivative. If it's in the first case, we can just plot an arrow to show that this is the direction of the derivative. And here we can also use one arrow. But in the last case here, we have on each point, right? If we select one certain point, then the derivative of the partial derivative, or the direction of the gradients is actually an arrow along that surface. Okay. So last time we also mentioned that the meaning of the direction of gradients. Okay. So actually, if we work on the surface of a function, and if we walk along the direction of the gradients, then we actually make sure that we can increase at the fastest speed. Okay, the gradients always point to the direction of the fastest increase of the function. So it's a simple idea. If we walk against gradients, if we go opposite of the directions where the gradient points to, then we are actually going towards the fastest decrease direction. Okay, so this is the most important principle behind the gradient descent algorithm, right? It's called descent, and descent means decreasing. So if we want to find the lowest points of a function, then it makes sense that we always choose to work along the direction that the function is decreasing with the fastest speed, right? It doesn't make sense if we go to a direction that the function increases. Like it's like walking on a hill, or go hiking to climb up a mountain or something. Like you should always choose the path that points to the fastest increase of your of the heights, right? Well, of course, we ignore all the plausibilities, all the practical issues in the hiking example, but in the abstract function example, it totally makes sense, right? So let's define the problem more formally. Our goal is to find the minimum or the minimal points of the cost function, j of theta. Because we have multiple parameters, our theta is a vector, right? So we should start, we don't know which theta will lead to the minimum point. So we will start with some random points called theta 0, okay? So the 0 here appears in the superscript. Remember that it is not, notice that this 0 doesn't mean the theta subscript 0, and theta subscript 0 is the one of the parameters, right? But here, the theta 0 here itself, it's still a vector, and the 0 here means it's our 0 or initial iteration of the algorithm. All right, and the second step is to choose a direction to change theta 0 a little bit, okay? And so that with the new values of theta, which is theta 1, the the output value of the cost function, J of theta 1, can actually decrease a bit from the previous cost function value. Okay? And of course, we want to choose the direction along which the cost function decreases fast, which is the opposite direction of the gradients. All right, and we will repeat the second step until the cost function no longer decreases significantly, and it will stop or be very close to an area in which the cost function doesn't change too much, and it's a very small value. And we will claim that maybe after the nth iteration, the current theta n is the minimal point. All right, and those final theta of n is the model parameters that we have finally trained. Okay, so next let's apply this gradient descent algorithm to the linear regression problem. And first of all, let's look at a simpler example to demonstrate how gradient descent works, using some more concrete examples of cost functions. So in this case, we look at a very generic quadratic function, right? J of theta equals a times theta squared plus b times theta plus c, right? The shape of it looks like this curve, right? And say maybe we start with a position at theta 0. Okay, so this place might be a little bit confusing because the theta 0, the 0 here actually, by putting a 0 here, actually means that it should be the theta, the 0 at the theta at the 0 iteration. Okay, all right, so that's our first theta. And if we compute the gradients of it at the current points, it should point to that direction, right? Because the gradients is a negative value, right? If we go towards right, the cost function will decrease, right? If we go left, then the cost function will increase. So the gradient is a negative value. And we want to go against the direction or go towards the opposite direction of gradients. Okay, and here comes the second issue. We can determine the direction, and we should also determine how large our step should be. Okay, so this step size is determined by the so-called learning rate alpha. This is one of the most important hyperparameters in machine learning, okay, or in gradient descent algorithms. So this alpha controls how big a step we want to move along that direction. Okay, all right. So the way that we update theta is theta 0 minus alpha times the current gradients. Okay, and why we use minus here is because we want to go against or go towards the opposite direction of gradients. So it's not plus. Okay, if we use plus, then the theta 1 will be at a new position where the cost function will increase rather than decrease. Okay, so let's use theta 0 minus alpha times the current gradients. Right, so it is actually where we go is actually indicated by this black arrow. That's where we should go. Okay, that's where the new theta 1 will be at. All right. And also alpha controls how much step we take. Okay, so now let's look at our next iteration. Okay, so theta 1 appears a little bit to the right of theta 0. So that's our new theta 1, right? So theta 1 is greater. And if alpha is controlled properly and it's small enough, then the theta 1 will be closer to the minimum points, because we know the minimum point is here. Okay, so if we control our alpha properly and don't make this step too big, right, then the theta 1 will be closer to the theoretical minimum points, right? And we will have the j theta 1 having a smaller value. So that is one complete iteration of the algorithm. All we need to do is to repeat this process and until a satisfactory theta of n is reached. Okay, so that is the so-called gradient descending algorithm. Okay, as you can see, we're approaching towards theta 2, theta 3, and it's gonna be reaching somewhere near the theoretical minimum points. Okay, so it's another problem that we need to define later. We want to know when to stop and how do we determine we're happy with the current solutions. Okay, that's a demo of gradient descent using a one-dimensional function. So the next, let's look at a different initial positions, right? What if we start at the right side of here? And we can notice that this time the gradient is a positive value, right? But our principle doesn't change. We should still move against the direction of gradients, right? Using the same formula. The theta 1 should be theta 0 minus alpha times the gradients, right? Which is indicated by this black arrow. That'll be our new theta 1. We can see the results, right? Theta 1 is smaller than theta 0. So if alpha is small enough, then the j of theta 1 should be smaller than j of theta 0, right? Similarly, we will repeat this process until we're happy with the results. So actually, no matter where our initial point is, it is the same principle, right? We would just always move to the opposite direction of gradients. Okay, that will, in this case, in this quadratic function case, if we do so, it will make sure that we will reach the minimum point. All right, and let's look at a slightly more complex example. Say if we have some function that has a two-dimensional input, right? That is our initial positions, where theta 0 and theta 1. It has two components. That is our initial position, indicated by these red dots, right? Our first iteration would be, we just compute the gradients, right? The gradients is now the partial derivatives. We need to compute the two components out of it, right? And the two directions here points to the gradients direction, right? And if we combine the two vectors, it's actually pointing to that red arrow in the middle. So we should move against the gradients. So we should follow the black arrow, right? And updates the parameters. So in this form of equation, right, we use a vector to minus another vector. So how we exactly compute the values is that these first components will be the results of these components minus alpha times these components, right? So because if we substitute the gradients into this form, we will have each component correspond to each dimensions. All right, so that is a one iteration, right? We have some new values, theta 0, theta 1, and the second iteration, we do the same calculation until we are satisfied without, until we are kind of pretty close to the theoretical minimum point. Okay. All right, so let's summarize the gradient descent algorithm a little bit. We simply start with initial values, and we will repeat the step of computing the gradients for each step, right? And use it to update the parameters, okay? And the process and this method we use to update the parameter is to go against the direction of the gradients, which is to minus alpha times the gradients. And alpha is the hyperparameter that controls how big our step is. Okay. And we will repeat until we find the final theta. Okay. And let's look at the linear regression problem for now. And we know that the cost function is in the form of summation of squares, right? The square of differences between the actual ground truth value and the predicted values. Okay, so this f theta of xi is the linear function that we have. Okay. So when we apply gradient descent, we will simply need to compute the gradients, the partial derivatives of this cost function with respect to each parameters. Yeah, so I see a question that's asked for an example to map the partial derivative form in real world. So the form that I'm showing right now is a real world example because the partial, the cost function has a concrete form, which is the summation of squares. Okay, so let's keep running this example and look at the forms of the partial derivatives. Okay, right, so it's really these two partial derivatives that we need to compute. And of course, in this simple example, we assume that there's only two parameters. Okay, there's only theta 0 and theta 1. All right. So for the simple linear regression, the cost function looks like this. We substitute this cost function right into here, it will be theta 0 plus theta 1 times xi minus y hat, right, raised to the power of 2. And if we take the derivatives of this function j with respect to theta, this is something we already did in the normal equation solution, right? We just treat the theta 0 as unknown and all the other variables as constants. Okay, so now we just replace this theta 0 plus theta 1 times xi with the y hat. Okay, so it's just a for a simpler notification, for a simpler notation. Okay, that's y hats. And for the second formula, the derivative with regards to theta 1, slightly more complex. What's inside is still y hat minus y. The outside there is a coefficient, constant coefficient xi left. Okay, so it will be a summation of y hat minus y height times xi. So that is the formulas for computing the gradients. Okay. So as for implementation in NumPy or in Jupyter Notebooks in Python, right? So basically, it's a summation of products, right? A summation of products is something that we can utilize the numpy.dot function to implement efficiently, right? We don't actually need to use a for loop to go through all these m examples, right? This summation, the counter for the summation is I, and I ranges from 1 to m. And actually, in our homework assignment, we don't need to use a for loop to go through over all these m examples. Actually, we can use one dot product to easily compute these gradients. Okay. So after we substitute the gradients into the form of gradient descents, we can like compute the new iterations, the updated values of the parameters. All right. So that's for the simple linear regression. And it extends naturally to the multiple linear regression because we have more than two parameters when we have n parameters, right? That's how the cost function looks like. And for gradients, we also need to compute n of those gradients. For the gradients with respect to theta 0, right? It should be this formula, right? And for theta 1, it should be the same formula with additional product term here, x1, right? For theta 2, there should be additional term x2 here. Until theta n. So actually, if we simplify the terms inside here into the the y hats, it will be actually the same format or the same formula as the previous simple linear regression example. Okay. And all these terms, they can be computed with the numpy.dots functions rather than using for loops. Okay. And we also update the parameters simultaneously. Okay. So that's a complete example showing how we can actually train a linear regression model using gradient descent methods. So it'll be particularly useful when your input has more parameters. Okay, when the input have more features than simply 2 columns. If you have just 2 columns, 3 columns, or a handful of columns or features, you just use the normal equations method to fit the model, right? It doesn't pay off if you set up gradient descent pipelines. But for larger models, the gradient descent models makes more sense. Okay. There are several common practical questions about gradient descent, which we will cover also later in the when we introduce more complex models. Okay, so for the first of all, the question is how to choose the initial values for theta 0. And a simple answer is that we usually use random initialization because we don't have any prior knowledge about the data and about the cost function. Okay, and second question is when to stop, right? That's a very critical question because we don't want the algorithm to run forever, right? There must be a point that we are satisfied with the results. And also how big each step should be. The learning rates actually will largely determine how fast our algorithm converges or whether it converges or not at all. Okay, so the choice of a proper loading rate alpha is critical to the training of models. Okay, and the fourth question, how many data to include in each iteration? That is a question we will face, especially when we have large data sets. In our assignments, we actually use a toy data set that has only 100 or so data points. That is a very small, tiny data set. So it's okay that in each iteration, we will put in all our data points. But when we deal with large scale of inputs, we have, for example, when we have hundreds of thousands of images, hundreds of thousands of words, millions of tokens, then in those cases, it doesn't make sense. We use all the data points in our one iteration of gradient descent. So it actually leads to a problem, a question of different types of gradient descents, right? So we will cover some of those questions today, and we will leave other problems to our future lectures. Okay. So a simple demo of a proper rate of learning rate alpha is that we don't want the alpha to be too big. Okay, using the same example here, if we start with the initial position theta 0 and the next updates become theta 1, right? If the alpha is too big, right, then the theta 1 would actually, on the contrary, it gets farther away from the minimal points, right? And the next step would even be farther away. So this kind of algorithm will never converge to the minimum points, right? And on the other hand, if alpha is simply too small, then the algorithm will be very inefficient, right? Right. It takes too many iterations to reach the minimal points. Okay. And for the evaluation, I would like to mention it a bit, although we will have a complete standalone lecture for evaluation of machine learning models. But for right now, we have a linear regression problem, and it's not, strictly speaking, it is not a complex machine learning models, at least. So we will use a special metric called residuals for measuring the performance of a linear regression model. So a residual is the differences between the actual ground truth value, ground truth target value, and the predicted values. Okay, the E is for error here. The E is the difference between yi and y hats. Okay, you can simply look at it as the the little segments here, measuring the differences, okay? But if we sum up all the e's, it will not tell us anything about the differences because they always equal 0 if we sum up the error terms. So we will use the residual sum of squares, okay? This formula is very familiar, right? It's just like the cost function that we use. And we will use the same quantity, which is the summation of the squares of the distances as a final indicator of how good your model is. Okay, so that's quantity will also be you also need to compute in the final in the linear regression model assignment. All right, so looks like we have plenty of times today. Let me pause